Greetings, welcome back to my channel. This is another video on the Racket programming language. Today we're going to just do another exercise on the tree data structure. So for convenience, I've set up this basic tree as a module to basically export some of these basic definitions so that I can access them in another file. I'm not going to go into too much detail into the module system. One, I'm learning more about it, and so I need to make sure I get more familiar with it before I really go into depth about that. But two, it's not really that important for their exercise. Just know that by doing this, all the functions that I defined in basic tree should be available here because I have required this file. So I have a basic typo here. So what I'm doing today is I'm going to go through and define another function on a tree, and I'm going to ask the question max depth, which is basically if I started at the trunk, how far up the tree could I go? Or how many stories does the tree have if I turned it into a building, for example? So again, I'm going to try to go from basics from the recursive definition. If the tree is empty, I'm going to go and say that it has 0 depth. If it's a leap, I'm going to say that the depth is 1. Otherwise, I'm going to say that the depth is 1 plus the maximum of the depth on the left and the depth on the right. And let's see if this loads in. And certainly it does. So what we're going to do is we're going to need to define another sample tree here. And in this case, I'm not going to worry about if this tree is actually ordered or not. It's probably pretty clear for you looking at this that actually this isn't, but it's not important to this exercise. So let us see what happens when we try to get the max depth of the sample tree. Okay. First of all, we made a slight error here. We need to do this. This is the condition we want to test. This is the value we want to return. So let's try this again. Third, this list contains too many elements. So there seems to be a little bit of a problem with how I've defined this tree. Let's make sure I've done this properly. And sure enough, I didn't. So that should be a proper tree. And this should be a proper tree. Let's see if this works any better. And it says that it is 5. And so checking on this, let's take a look here. Starting out here, that's 1, 2, 3, 4. So 1, 2, 3, 4. Going in here, 1, 2, 3, 4. So I'm kind of curious if this is actually correct. Let me see if I can think about this. Gone 1 step, 2 step here, 3 steps here, 4. Seems that the proper depth should be 4. So I'm wondering if the tree is a leaf, that the proper thing to say is actually that it has no depth. And certainly that makes sense. Basically, if we think about the max depth as the numbers of steps that we had to take before we could get to a leaf, well, if we're already a leaf, then it is 0. It's the same as if we're empty. So this makes more sense to me. So now what I need to do is just to double check this. I can basically go on and now add depth to this tree. Let's see if I still got the definition properly. Again, one of the things I seem to have not balanced things properly. 2, 1, 3, 4, 5. Is this indeed a tree? Now this, however, is a tree. And indeed, yes, it seems that now that it can go down an additional layer, that this does work. So in this case, this was a fairly straightforward type of operation. The reason I bring up this example is that now one could ask the following is, if I had a tree and I wanted to do beg your pardon. If I had a list of elements and I wanted to turn them into a tree, how could I do that? And when you think about it, there's tons of ways you could do it. But let's say I wanted to do something that made sure that the following was true. That basically for every part of the tree, so max depth for the left part of a tree was either so the max depth of the left part of the tree and the right part of the tree at every step for that tree, this is always true. And what this is you can think of this as this tree being balanced. And what it means is that it pretty much has the same amount of leaves on the left side as it does the right side. And that actually is a fairly useful type of thing to want out of a tree, in terms of there's lots of properties that would be very useful for. For example, if we're doing a search tree, we would certainly want to make sure that that is true, so that we add an order tree, if it's optimally balanced as possible, then we can make sure that searches on there work as well as possibly can. The thing about that is that ensuring this is actually a very difficult proposition. And I won't go into the algorithm that actually allows this to happen until we get further on into this series. But what I want to point out is that one of the difficulties with developing software is you hit walls of complexity. And what that means is that you literally go into a data structure or certain domains and you have a lot of things which are fairly simple. And then you come to things where you have something that is actually fairly easy to explain, that basically you have this constraint that you want to have, and you actually want to say, well, how do I make that possible? And it turns out the way to do that is exponentially more difficult to try to figure out. It doesn't fall out very naturally from the definition of a tree, and so it takes a lot of effort to figure out how to do in an optimal manner. Now, if we had decided that one of the ways we could do this is actually to literally go in, and if we know how many items we have in advance, so that we could literally, basically what we could do is we could do the reverse of figuring out if a tree is ordered by basically taking a list, basically sorting sorting a list, and then finding a procedure that is list to ordered tree. And of course it would be a sorted list or ordered list. We could define this procedure. And for those of the more senior among you, then you might think about how to go about doing this. It's actually a fairly simple application of a divide and conquer algorithm, in which you basically go ahead and split the lists into two parts. And since we know that it's ordered, we can then do that to build a tree until we get down to the base cases. As a bonus video, I might do this, define this operation. But that only works if we really know that what all the elements are. What if we want to do it such that as we add to a tree, that the tree that this returns is also balanced? And that's where this becomes very tricky, because you actually need to go in and basically there does have to be rebalancing operations. And the pathological case that you could do, which would literally be to take the tree and basically take the tree, flatten it in order, add that value into the list so that it's ordered. So that's fairly easy to do. And then turn that back into a tree. That technically would work, but would actually be very inefficient. We would want, basically, in this case, for the operations for adding a new value to a tree, not to cost the same as sort of the entire tree plus one object. That doesn't necessarily make sense. What we want to do is we can say, is there a better way of adding that doesn't do all this extra work? And this goes from a programming problem that you might be able to, eventually figure out. If map and flatten trees are fairly simple to figure out, all the way to something that if you didn't know the algorithm to do this, it would be very difficult, if not impossible, for you to figure out how to do it without having to resort to literally going back to, oh, well, I will just actually have to do what you said, which is basically turn the tree back into a sorted list, insert that item, and take that sorted list and turn it back into a tree. So one of the things to be careful about, and one of the things that is most difficult about programming, is to know when these large jumps in exponential complexity can happen, because they're very subtle at times. It seems like certain operations should be very easy, but when you add one or two more twists to them, they can become much, much more complicated. And so much so that there are some people that would argue that at the very minimum, sometimes you have to get away with just doing the very obvious worst case thing until you really understand what the best case thing is. And so if you really don't know what the algorithm is for a data structure to do stuff, and you can't find an obvious answer that someone who has way more experience in algorithms or data structures has, you might have to do it the very, very dumb way to get it done at all. And not only that, but then it becomes important to understand when even the dumb way just will not work. That at a certain point, it'll just be too complicated or take too much work to do. And you actually need to think about another way of doing things. Now, in real world programming, when you're a professional, this does not happen as often as you would think. And the reason being is that there are so many libraries and frameworks and data structures out there in which people have already thought about these problems and make sure that you have the tools that you need to do a lot without ever bumping into these fundamental problems. So again, the vast majority of programming that you're going to do will be using these existing algorithms, data structures efficiently, and not having to worry about how to define new ones. And not only that, but there's certain large tools that the reason that they exist is to make a whole large category of problems easy to manage so that you don't have to manage yourself. The reason we have relational databases is just so that they can provide all the infrastructure you would need to make things like sorting and ordering and doing all the things that you would want to do to find information as efficient as possible without you having to go off and implement the numerous types of algorithms and optimizations necessary to do that kind of work. So again, it's more interesting to note from a theoretical standpoint that these types of things can happen when these bumps on the road are, but in practice, they don't end up happening too much. Now, that being said, they sometimes will bump up. I have seen people where they unintentionally have programmed themselves into a corner where they have a set of code that really is very poorly inefficient and bumps into some problems once they get past a certain amount of data. For example, it's like, well, it worked fine until we had 1,000 customers and then it blew up. That can happen. So hopefully this gives you an idea of a little bit more about how the recursion works. One of the things that you can do here is as an exercise is to generalize this so that you could use this to define the minimum or the maximum of depth, depending on the procedures that you pass in here. Hopefully that should be a fairly obvious change. And also, if you do a little bit more research online about how to make it a balanced tree, such that every time you add to that tree, it constantly keeps itself as balanced as possible. Anyway, thanks for watching, and see you in the next video.